Okay. Section 4.4 calculus. Begins on page 219. This is called modeling and optimization. So in the previous three sections, we've learned how to use the derivative to find maxes and mins. Yeah. And now we're going to apply that to story type problems. However, because our calculators are so good at finding maxes and mins without using a derivative, I will not hold you to that. What's going to be much, much more important in this section is that you can take the information given and put together something that you can optimize. In other words, you got to take the story problem. You got to figure out what sort of an equation you can use to answer the question. And optimize means to either minimize or maximize something. Okay? It's going to be a lot more together based on previous math knowledge than it is, once you finally get that done, than it is using the calculus to find the maxes and mins. You can use your calculator if you want. Okay. Just a little blurb from the author right at the very beginning of page 219. It says, while today's graphing technology makes it easy to find extrema without calculus, which we discussed, the algebraic methods of differentiation were understandably more practical and certainly more accurate. What? The algebraic methods of differentiation. Oh, okay. Our technology makes it a lot easier to find those maxims and minimums, but in the past, the algebra made it. You find the derivative, set equal to 0, find the critical values, put it on a sign chart, and all of that stuff had to be done by hand, all the plugging in and everything. And then they defined the maxes and mins. What?
Did you have to do that?
I did. Yeah, because I didn't have a calculator that would graph where I could say, oh, there's a peak, I'm gonna go find it. It's very easy calculus to do it. Yep, I'm a generation removed from this technology. Indeed, one of the oldest applications of what we now call differential calculus, predating Newton and Leibniz, was to find maximum and minimum values of functions by finding what horizontal tangent lines might occur. We will use both algebraic and graphical methods in this section to solve max-min problems in a variety of contexts, but the emphasis will be on the modeling, that's what I mean, putting things together. That process that both methods have in common. Here's a strategy you can use. I don't think we need to outline a strategy. I'm just going to demonstrate it for you. If you want to come back to this and see how it applies, or you forget what to do next, or whatever, you come back to this problem box. I'm not going to spend any time on it. We're just going to dive in and do some problems. Okay? Example 1, this is to get your feet wet a little bit. This isn't going to be very hard. You probably even know what it is before we start, but then it's going to get pretty tough pretty quick. So, first one says, find two numbers whose sum is 20 and whose product is as large as possible. Find two numbers whose sum is 20 and whose product is as large as possible. You'll see me write that a lot. Whose product is maximum, okay, or minimum. I'll just put the word there so that we know where we're headed. Okay, so if I want to maximize that and I want to use technology to do it, I need this to be written in terms of one variable only, which is why this is here. It's not very hard. So if I replace y with 20 minus x, you could probably do that without even writing this down. Just, if one of them's x, then the other one's 20 minus that. I gotta have 20. So either way, whether you write it down or not, and this over here is what we want to maximize. So whatever it is you're trying to optimize has to be written in terms of one variable, and that's the hard part of this stuff. This isn't very hard. And so we have times replacing y with 20 minus x equals a maximum. What we can do is graph that now, and it's in the form that it's in. We don't even have to do any foiling out or distributing or anything. I shouldn't say foiling. Distributing. And then you plunk that in your calculator and adjust that. Another part of this that's going to be kind of tough is you adjust your window until you can see the maximum of that equation. If you always start out on a Zoom standard screen, you might be a while getting what you want to get. But what I get on a Zoom standard is not much. Just that blue line. But we know this thing's a parabola that's turning, that's opening downward. which means that I've got the left leg of that thing. I got to go way out to the right. I got to go way up. So I go to my window. I'm going to go, let my x's go from -10 to 100 by 10s. And I'll let my y's go from -10 to 500 by hundreds. Oh, that was a little much. That's what I get with that monster window that I built. But I can see the maximum. I mean, I just stuck down here in the lower left corner. I went got a little carried away with my table or my window. So I calculated maximum. Oh, so negative. So there it comes. 10. What you might have imagined. Both of the x and the y values are as big as possible. So if x equals 10, then y equals 10. And the maximum value is 100. That wasn't too bad, right?
No.
Okay. Now we're going to jump into something that you might not have considered before. And when people get frustrated, they say, who would ever want to do that? That is not a question that I'm going to be prepared to answer. We're going to do it. So don't get frustrated. Next question, please don't turn a page for the solution. Let's just see if we can figure it out without seeing how AE does it. It says in example 2, and there's a picture to the left of it. See, I'll draw it on the board too. It says, a rectangle is to be inscribed under one arc of a sine curve. What is the largest area that the rectangle can have, and what are the dimensions? So,
Sine curve.
yeah, one branch of a sine curve. So let's take the first one. Graphs like this, as you know, and it goes up and it comes down, it goes around, periodic like this. We're talking about one right to there. And we're going to put a rectangle under here in such a way, and we're going to try to figure it out, in such a way that this rectangle's got the biggest possible area. You at least understand what we want to do. Okay, let's get some details here. What is this? I mean, at one branch, where does it land right here?
Pi.
At pi. Okay, so we got from 0 to pi here that we're dealing with. And what is this up here?
1.
1. So when we actually do graph this thing, it's going to be a really tiny window. The numbers are very small here. So, oh, and we all agree, I hope you do anyway, and I think it's something that probably doesn't need to be mentioned, but I'm going to. This branch, every piece of the sine curve as it goes above and below the x-axis is symmetric. So, just so you know, this is what I want to maximize. I want to take the base of the rectangle times its height, and I want that to be a maximum. And I can't put that in my calculator now because I've got no context. We don't have a b and an h, and besides that, it has to be in terms of one variable. So, how far is it from here to here? I'm not looking for a number. X. That's how far it is. Okay?
Good.
Then how far is it from here to here?
Pi minus x.
Yeah, pi minus x. Because of the symmetry, I know I didn't draw it very well symmetric, but you see what I'm saying?
Yeah.
See what he's saying?
Yeah.
Okay, so this location right here is pi minus x. So what is this distance from here to here? That's I'm going after the base, in case you're wondering what I'm doing. What do you think?
Pi minus
2x. Two ways to think about this. I came in x from here and x from here. I've used up 2x's here, so what remains is the pi minus 2x that I came in. That's the geometric idea of it. Besides that, to find this length right here, I could take the far one, which is pi minus x, and subtract the near one. That'd give me pi minus 2x too. Have I lost anybody?
No.
Okay, then the base can be replaced with pi minus 2x. Now I need the height. This distance right here. That should correspond to this right here, that point right there. I went out x, how high up do I go? Nope, nice try. I mean, it is y, but we can be more specific than that. Sine x. Whatever the x is, that place on the curve is the sine of that.
Yeah.
Right?
Yeah.
Okay. You have to start thinking like this. It's always happened. You guys aren't the first ones to do this and go, I don't know. And then I say sine x, and I go, oh, yeah. Okay, so the y value at x is the sine of x. And now I have something to graph. Be sure you're in radian mode. I always say that. I'm teaching trig right now. We're jumping back and forth all the time, so I'm always warning people.
It's a weird one.
Is it? Kind of weird looking? Okay, if you go to a standard screen, you get something wild and crazy like this. Is that what you did?
Yeah.
Let's think a little harder. What's the most that x can be?
Well, oh,
Not pi. Pi halves. So I'm going to go to my window. I'm going to let x go from 0 to pi halves. That's the most it can be. So if we think about the domain a little bit, we can not have to look at such ugly graphs. I'm going to go by pi halves. Ones is fine. And then what's the most that sine x can be? I'm sorry. What's the most that, well, just tell me to guess a little bit. What's the most that this curve could contain under it? Then you might think, okay, well, that's 1 by pi. It's 1 tall and pi wide. Even if we use that entire rectangle, it can't be more than pi. So that's pretty tiny too. So on the y's, we go from 0 to pi. That's what I'm going to do. And now I'm going to graph it and look at only that piece of it that pertains to this problem. And I get a graph that looks like this. And if you look at it carefully, it is not symmetric, but it does have a maximum.
Yeah.
So we calculate a maximum. Notice we're not doing any calculus. If we did, we would have to derive this, set it equal to 0, and find the x values where it's 0 and plug it into the original. But with this, we get the point, not the point, just the x value, we get 0.71.
yeah.
Okay. So when x is 0.71, we get a maximum area of what? Anybody? And it is. It's 1.122. It's sitting right there in your calculator. Because what did we graph? We graphed area. I mean, I put max here, but base times height is area. So this is your y value in the graph that we just did. This is your y value. The x value is this little chunk right here. We found that x is 0.71 coming in, and it produces an area of 1.122 because that's the y value of that maximum. Does that make sense to you?
Yeah.
Because the y value is area, and the maximum area is 1.122. But that's not all it has to do. What is the largest area that a rectangle can have? We found that. And what dimensions give that area? This is a little harder than you think. If x is 0.71, then the base is pi minus 2 times that. Now remember in your calculator that right now, if you haven't changed anything, right now stored in the x mailbox is this number. So you don't have to write it down and you don't have to retype it or anything like that. Just go back to your home screen and type in pi minus 2x. Actually type 2x and it will calculate with the x that's most recently been put in the box. So I get a base from here to here of 1.72 about. How do we find the height? Take the sine of x. Isn't that the height? Didn't we agree?
Yeah.
And x has still got that value in that mailbox. So now you can just go sine x. Do you see what I'm saying? And that's going to be 0.652. So if you know your calculator really well and what it's capable of and what x, stored in there, whatever, we found that x, you can just calculate with x as long as you don't move the cursor around on the graph screen. You'll remember this until you change it to something else. And so we get dimensions of 1.72 by 0.652, and the maximum area for that is 1.122. I'm going to check that out just to make sure. 1.72 times 0.652. I get 1.121.
Yep.
So that's because these are truncated. These have been approximated. Okay. So the moral of this one is, and you will see this many times, if you're going to try to fit something under a curve, to find the height, you evaluate it at that x. You evaluate the actual curve. You evaluate it at that x value, which means, in this case, sine x. And then you got to think about the symmetry of this. You got to come in on both sides. You got to figure out what that thing's going to be too. But most people have more trouble with the height. And it's just the function. Evaluate it at x. Okay? All right. Now we're moving on. We get the same thing he got? 1.12, 1.72, 0.65. Yep, cool. Now, you're going to see some real geometry next. We're going to do that exploration 1. This is an interesting objective because it's nothing, it's no geometry that you've done before. But your geometric experience will help you wade through it. Here's what's going on. It says a cone of height h and radius r is constructed from a flat circular disc of radius 4. And the way we're going to construct the cone is by removing a sector, AOC, the white part of that sector you see there, whose arc length is x. That's weird. And then connecting the edges, AO to OC. What arc length will produce the cone of maximum volume? That's a loaded question. That's a hard thing to do. This is what we're going to do though, something like this, okay? And you take a circle, and this is radius 4, right? That's what he said.
Yeah.
We went through there. And when we put these two things together, circle, radius 4, this is 4 from here to here. And we're going to attach, cut out that sector, and we're going to attach these two together like this to form a cone. And we would tape it, and it looks kind of like, at least right now with what I cut out, looks like the traditional Chinese hat. Maybe a little too deep for that, but okay. And what we intend to do then is to try to figure out how long it is from here along the circle that I cut out, along from here to here, how far it is from here to here, so that the cone formed has a maximum volume. We want to find this distance. So you understand what we want?
Yeah.
Don't know how we're ever going to tackle this.
No.
Okay, that's fine. That's good. As long as you know what we want. We want this length. And so by the time we end up writing our equation that we want to maximize, it's got to be in terms of x. This x. That could be a daunting task. Okay, so if you will look, those of you still following on the video, if you will look on the bottom of page 220, they've got the paper drawn. They're drawing A and C together to form the cone, and then they've got the cone drawn. And the cone's dimensions have a radius of r and a height of h. And because of the way we folded it up, we understand that this slant height right here is 4. This is the same as the radius of the original cone. Okay, now he's going to lead you through here, but he's not going to give you any answers as we go along. He says, show that r is 8 pi minus x over 2 pi. So he's not asking you to come up with it. He's asking you to believe it and to convince yourself it's true. 8 pi minus, what was it, 8 pi minus x?
Yeah.
Over what?
2 pi.
I'm sorry?
2 pi.
2 pi. And remember, r is, so I'm going to go ahead and draw the cone and see if I can draw it reasonably well. Remember that R is the radius of the cone once it's been formed. This is R, and this is the R we're talking about right here. And I want to know if you understand why that should be the case. So, what is the circumference of this circle with circular base once we get the thing formed? It is 2 pi r, isn't it?
Yeah.
Then isn't r c over 2 pi? That's where the 2 pi comes from.
Yeah.
But isn't the circumference of this, minus x? So when we form that together, this circle formed down here is the same as this length right here.
Yeah.
Which is the circumference of the original circle minus x. What's the circumference of the original circle? 2 pi r, r is 4, 8 pi.
Yeah.
So this is the circumference of the original circle. We subtract out that arc length x, fold it up, and now we've got this circle whose circumference is 2 pi r. So we divide by 2 pi, and the r for our cone ends up being the circumference, which is 8 pi minus x divided by 2 pi. Be tough to come up with on your own though, right?
Yeah.
Okay. It says, also convince yourself that h is the square root of 16 minus r squared. That one's not so hard. Because when we draw this, and this is 4, h is h squared plus r squared equals 16. Turns into that when you solve for h. You okay with that?
Yeah.
That means that h is actually, because remember, we can't have this in terms of x and this in terms of r. That means that h is actually 16, big 16, minus 8 pi minus x over 2 pi squared. Replace r with what it's equal to. So this is because of Pythagoras. But I need to get r and h all in terms of x being the arc length, which is what we've got here. And we replace this r with this right here, with what it was up there. So now I've got everything in terms of x. Now I just have to remember the volume of a cone because that's what I want to maximize. The volume of a cone is equal to 1/3 pi r squared h. Because it's pointy, we divide by 3. Remember that? Pointy things are 1/3 of what they would be if we just left them spread out in geometry, you recall?
Sure.
Okay, so I've got my constants all lumped together there. So now I've got pi thirds, parenthesis, 8 pi minus x over 2 pi squared times the square root of 16 minus 8 pi minus x squared. Oh, no. I'll put the square on the whole thing over 2 pi squared. That's my volume. I don't want to maximize that. So the problem isn't the calculus. It's using parentheses appropriately to type the dang thing in there. You know what I'm saying?
Yeah.
And before we do that, just like before on when we did the one with the sine curve, we were trying to put something under it. If we just graph that on a standard screen, we got a whole bunch of crap. And we only wanted to look at one part of it that made sense. So I want you to consider that for a moment. I want you to think for a minute and consider what our window will be. Remember what x is. Remember what x is. It's that little piece of arc. It's the length of that arc that we cut out. Remember? And so what's the minimum that can be? And the answer is 0 when you got a flat piece of paper and no cone. But it can't be any less than 0. So I'm going to say on this thing that the domain for x, which is the x values of work, the domain is going to go from 0 to, now what's the very most that x can be? Eight pi. Because the very most you could do is cut out the whole thing and then you have no cone either. So we're talking about a no cone, but it will start here. We're talking about a no cone here and it will end there, but it won't be any bigger than that. Okay, so that's your domain. I want you to think about that when you set up your windows. And then think about what the volume might be. Now this just takes some ingenuity, and you can always adjust your Y's. But think about what the volume might be in cubic things if, I don't know, that's a really hard thing to think about. Just give me a ballpark, big ballpark idea of what you think the maximum Y could be. Just give me an idea. Is it 2 million?
No.
Is it 200? Is it 100?
Okay, if the,
Talk about the volume of this cone,
oh, the volume,
because that's what I want to figure out how to set my Y's to at least get started.
maybe like,
Keep working on it. Okay, this is just your like.
Oh, I think it's a lot more than that, but we could try it. We'll try your 20 and see, and then we'll see if we have to adjust it. Okay, so we'll try it like that. You just got to guess at this. This one you don't, because we know what X is. We know what it can be. And so if we can get the right X's, we can look at the piece that we can see and then just expand our Y's if we need to. Won't come down, like I should have. I'm not going to do it. But it is. So make your best effort at typing this in using parentheses appropriately the way you know you should. And let me warn you about one thing. Make sure you wrap parentheses around this and this and this and this, because otherwise it will only divide the numerator by 2 and multiply the result by pi. Do you know what I mean? So be careful with parentheses there. There's going to be a ton of them. I'll see what I can do. I'm not sure. I think I can.
It'd be very much appreciated. I'll treat them good.
That guess of 20 wasn't too far off, Akira.
oh, really?
Yeah.
That's not.
I'm blowing my window still.
What?
My window is still.
Oh.
Pretty sure my calculator is struggling, nothing's happening.
Did anybody get a maximum of 4.612 and a volume of 20, a maximum X, I'm sorry, an X of 4.612 and a volume of 25.79? Haven't gotten there yet, huh?
I'm just about fine.
Okay.
Maximum. Uh, 4.61 and
25.8.
25.8. That was a lot of parentheses.
Okay.
This is so tedious.
Mine's not even doing anything, it's just frozen. It's doing nothing. I go back to Y. I go back to graph.
Wait, what did you get?
Graph, I bet it's
For
The maximum?
4.61
Just go from 0 to.
and 25.8.
Go!
0 to 85.
Got it.
Let this go from maybe 0 to 30 is fine. Still nothing. Should be doing fine. I don't know what the deal is on that.
I think we found the limit where my calculator just dies.
This isn't really too bad for it. I just let it keep breaking, see if it, does it give any indication that it's working?
No, it usually has that weird little
Yeah.
loading bar at the top, but there's nothing.
I don't know why that is, that's weird. Did you get it, Akira?
I got it, yeah.
Okay, now, rather than do this directly and muscle really through it, it seems to be that this part right here is the hard part to put in, and you have to do it twice, and you have to square it.
Yeah.
So what you could do, if you recognize that, is find that by using the by parentheses, a pi minus x on your home screen, divided by 2 pi, like that. And then store that in something, like a. Store it in a, then when you type it in, you
How
can
do you
just type,
store something?
I'll show you in just a minute. So y equals, and then you could do the pi thirds in your, the y1 you're doing in your.
Yeah.
And then parenthesis a squared, square root of 16 minus a squared. That would be a lot easier to put it.
Oh, that would.
You do it in little pieces. Now, the way you store things is in your, those of you watching this too, it's just above the on key. And so what we will do is we will figure out what that 8 pi minus x divided by 2 pi is in the home screen. So go back to home. So 8 pi.
What's X?
Oh yeah. Guess maybe we can't do that.
Maybe you could store it in Y1. And then in Y2, you could just do pi thirds
You could do that
Y1 squared.
I'm so
and then turn y1 off.
Yeah.
Yeah, this was such a great idea. And then you said, what's x? That's what we're trying to find. Crap. You might be able to do that, Akira. Let's try that. Let's go to y equals, and I'm going to leave mine in there the way it took a long time to type, so I'm just going to turn it off. But in y2, I'm going to type in this thing, which is parentheses.
Oh, that's why I wasn't graphing.
Y minus x. Why not? Divided by 2.
Okay. Well, now I'm looking at it.
Was your window way too small?
No.
You had the graph off.
Yeah, I had the graph off the whole time.
Oh, you had the equal sign turned off. Okay,
Yeah.
all right. And then, so this is what I've got. I don't know if you can see this, but I've got that mess because I'm not willing to erase that yet. I know it's correct. And I've got that little piece in Y1, and so now, and I've got them both turned off because I want to see those. I want to see if what she's suggesting we do will work. So I've got both of these turned off. If you're looking, the top one is what I originally put in, and now I'm putting in that weird thing that I circled up here in Y2, and I'm turning them both off so I can't see the graph. Then I'm going to type in what we did here, which is in Y3, pi divided by 3, parenthesis, and then I'm going to go to my vars key and grab Y2, squared, and then square root 16 minus Y2, go in my vars key, squared, and get out of that and graph that. See, yep, it's giving me the same thing. Very good, Akira. That's how we're going to have to store things with variables, and it was in the y equals key. So I get the very same graph I did before by doing this in pieces and letting this stuff in the circle be Y2, turning it off, and then typing in Y3 using Y2 for the vars key. So that'll work. If you're struggling to try to make sure you got it mixes right, you can do it in little pieces. Okay, that's crazy, huh?
That was a wild ride.
Yes, it was. Very cool.
Wow.
And now I know multiple ways to break my calculator.
Yes. All right, so now the next one's gonna be super easy because we've done this probably at least 3 times in Algebra 2 and pre-calc and maybe even trade out. So we're gonna take a piece of cardboard, cut squares out of the corner and fold it up into a box and find out try to maximize the volume of it. Pretty easy, do we need to do it?
Yeah, let's do it.
I'll do it real quick. Okay. The original cardboard that you can see on the top of page 221, it's already had the corners cut out of it. The original one was 25 by 20.
We did this.
So if I cut a square out of each corner that's X by X each time, that means that when I fold up those flaps, that the new length is 25 minus 2X, and the new width is 20 minus 2X. And the height is X. Have I lost anybody on that? So by the time I open up this box, I fold it up. It's kind of look like a pop can box, I think. At least that's the way they have it drawn. So by the time I fold up the box, I've got this going on, and this is 2X in from the original. So this is 20 minus 2X. This is 25 minus 2X. And when I fold it up, I fold up an X. Is that okay with everybody?
Mm.
So the volume is already written in terms of X. The volume, which is length times width times height, is going to be X times 20 minus X, 2X, times 25 minus 2X. Now, before we begin, this is probably the most important part of this modeling business, is figuring out the domain that works. Because you don't want to look at this entire cubed graph, and it will be a cubed graph, a cubic function. I don't want to look at all of it, only the part that pertains to this. So what is the very, very most that X can be? When you think about cutting out those squares, what's the most it can be?
25.
10. Because the original square was like this. The original rectangle was like this. And you're going to cut squares in. If this is 20, you can't cut in more than 10 in both directions on the short side.
Oh, yeah.
Does that make sense?
Yeah.
And that's what X is how far you're coming in on the sides to cut a square. So the very, very most that X can be is 10. So you need to think about that, those domains. Go to your window, go from 0 to 10 by ones. The volume, however, that's another guess. Do you think it's in the millions? Thousands?
No,
Hundreds?
closer.
Probably hundreds. And here's why I say that. Because X is probably it has to be a single digit number if it's less than 10. So you've got a single digit, probably times a 2-digit. 25 minus 2X is probably still going to remain 2 digits. Now, if it was as big as possible, this would only be 5 right here. But I'm thinking it'll probably be a small 2-digit number. This will either be a small 2-digit or a large 1-digit.
Yeah.
So if you take a 2-digit, small 2-digit times a small 2-digit times a 1-digit, you're going to get into the hundreds.
Yeah.
That's what I'm asking you to consider. And so I'm going to let my Y's, to begin with, I'm going to let my Y values go from 0 to 250. I'm just going with that. Okay.
It's way bigger than 250.
Oh, is it? Okay. All right. Time will tell. And so I'm going to clear out, I hate to do it, but I'm going to clear out all my other stuff from the previous problem. Type that in instead.
That'll work.
X parenthesis, 20 minus 2X, 25 minus 2X, and graph on the window that I chose. And you're right, it is way bigger than that. So I got to go to my window and at least double my Y's, probably more like 700.
Oh, it's over that.
Even that, okay, so,
I suggest just setting it at 1,000.
okay. Go to 1,000.
Yeah.
At least I was seeing more and more and I was getting an idea, so we just keep playing with it. Also not symmetric, but also has a maximum. Calculate a maximum. And it looks like we better cut in about a little bit more than 3.5 inches to make our squares. And we'll get a volume of 820.53. Is that what you're getting?
Yeah.
Yep.
Okay. Another variation on this problem is that they might not say maximize the volume, but they might say what X value, what I need so that the volume is exactly 700. So you go back to your Y equals and type in 700, graph that, and find those intersect points. You could have an X value here and get a volume of 700. You could have an X value here and get a volume of 700. They're different shaped boxes. You have to decide which one you like best. But that's a variation on this problem. Sometimes we don't want to maximize it. Sometimes we want the volume to be a particular amount, and it comes up twice. Okay, next problem is like Anduits, but not quite the same. So again, don't turn your page. On the bottom of page 221, we are going to design a can now, a cylinder.
Oh, no.
It says you've been asked to design a 1-liter oil can shaped like a right circular cylinder, a can. What dimensions will use the least material? You can a 1 liter oil can. That's all you get. And what we have to do now is minimize the amount of material to make that can. But it's gotta hold a liter. Now, do you measure distance in liters?
No.
What do you measure distance in?
Volume.
Volume is in liters. What do you measure distance in? Or things? Well, stick with the theme, folks. It's metric.
Oh, yeah. We'll go
Centimeters or meters?
Centimeters or meters for this.
Yeah, I'm gonna go centimeters only because, if you'll remember from science, 1 liter is 1,000 cubic centimeters.
Yeah.
So I'm gonna let my linear measurement be centimeters. Okay, so here's all we've got. We have a volume, a prescribed volume, and the volume of a can is pi r squared h. It's the area of the circle times the height. That's how much it fills it, right?
Yeah.
Okay, and I know that has to be 1,000. That's what we're gonna put in each can. Okay, so there's my volume, but what we wanna minimize is surface area. Right? Remember the surface area of a cylinder?
Or
Oh, that's you're thinking sphere. I'm thinking can, cylinder.
oh,
Don't you need like the area of like the square part?
You need the top and the bottom circle,
so
and each of those is pi r squared. Does that make sense?
Yeah.
Top and bottom is gonna be 2 of those pi r squared circles. The rest of the can, if you cut it from top to bottom and open it up, is like it's a rectangle. If this is the can I'm talking about, this is my cute little can, the 2 yellow circles are already up there, there's 2 pi r squared, but then there's this part right here. And if we cut it like a soup label on a can like this, we cut it down the middle and open it up, you get a rectangle. And the rectangle's area is the circumference of the circle. That's the length, right?
times the height of the can.
Times the height of the can. And the circumference of the circle is based on the radius of the can, which is 2 pi r. So this thing is 2 pi r across the top, 2 pi r times h. I'm going to add that to the circles. Does that make sense?
Yeah.
Okay, that's the surface area. That's what we wish to minimize. The problem is that I have surface area in terms of r and h, and I can't put anything in my calculator when there's more than one variable, which is where this guy comes in. So my question is, would you rather solve this one for r or h? What? Which one will be easier to solve for?
H.
H, because if we solve for r, we're going to have a square root. Okay, so if I put 1,000 divided by pi r squared, that will be h. And I can replace h with that, and then I'll have a statement in only one variable.
Yes.
Okay, so the surface area by replacement there is going to be 2 pi r squared, because it's in r, plus 2 pi r times 1,000 over pi r squared. Now, you could plunk that in your calculator just like that. It's not really very hard to simplify that last thing just a little bit first. That's going to be plus the 2 times the 1,000 is 2,000 on the numerator. 1 pi will this pi here, and one of these r's will cancel with one of these r's. Nice.
Yes.
That's easier to type in.
Quite a bit.
Now, before we start typing, everybody wants to grab that calculator almost immediately. Let's think about it. Do you have a feel for, inside your mind, the size of a 1 liter can or a 1 liter volume of stuff? You get 1 liter soda, right?
Yeah.
About like this. And so if we were going to make a can, maybe a little bit squattier, we're talking about like this,
Yeah.
right?
Yeah.
And just think about centimeters. Centimeters are only that long. Tell me what you believe that R might possibly be. I mean, it could be anything, but I don't want an R of 0.2 centimeters. Give me an idea of, because this is your domain here, of a domain here that might be reasonable. Certainly the radius has got to be at least 0, right?
Yeah. 0 to 8, 10.
You wanna go to 10?
That's a lot though.
That's a lot. 10 would make that, if you made a can like that with a 10 centimeter,
It would be
thinking
super-
about the size of a liter, a 10 centimeter radius is going to be
It'd be super
that
flat.
big and be super small, but it could be.
Yeah.
I'm saying that's a reasonable thing, okay? Range, meaning the surface area of the can. Now, that's a hard thing to guess at. The range means how many 1 centimeter square stamps could you stamp all over that thing without overlapping? That's what we're saying. And that would obviously be 0 if we didn't make one, up to, give me some idea. Hundreds of thousands? Less? 100,000? 10,000?
Some hundreds.
Hundreds. Okay, give me hundreds. Let me get 500. There you go. Okay, so that's what I mean. You got to kind of guess at that, so you can at least get your window started. Now try it.
Check where it did it. We're way too low. We're way too.
Yeah, you guys are low.
No, I hate when
Well,
I'm just gonna keep it. at
Window
whatever.
0 to 10 by ones.
how would you guess?
0 to
I already
500.
figured out how large or high you need to go.
2 pi. Dang it, I always do that. I gotta put my glasses on. I always hit that E instead of pi. Ugh. 2 pi x
Oh, what the-
I did something wrong.
2, 1, 2, 3.
What'd you do?
We both did something very wrong.
No, that's what I got.
Oh, so it's
Why
like, we're
is
just
it a
trying to
minimum?
find a
not a
minimum.
maximum?
Oh, because we're trying to find the least amount of material that we can.
Oh, I was like.
Uh-huh.
So we chose this window and nothing showed up, right?
Yeah,
What does that mean?
we're too small.
We gotta go bigger, because if we're trying to minimize something, we're looking at the bottom of something and I can't see the bottom yet, which means we have to go up higher to see it.
Yeah.
So we go to the window and we go to 1,000 maybe, see if we can see that.
Yeah, you can see there.
Oh yeah, there it comes.
Quite a bit.
But we missed it with our 500 guess, and I was fine with it, Kira, that's fine. But you gotta understand that this graph, since we are minimizing it, has gotta be the bottom of something. Perhaps we can't see the
I
bottom
just
here,
want to let you guys know that,
so you gotta go higher.
all of you have donated so far, thank you so much, but guys, we can do better. Like, let's bring in the money. And to help with that, tomorrow we are gonna do your second hour, class competition, where if your second hour brings in the most money, you guys.
There's
get
4 of
to-
us.
and,
It's not a straight shot, it's per capita.
Tomorrow, so if you bring $2 to the office and get a stamp, you wear a hat, and we're also gonna have, each grade is gonna have a goal of $100, and if you guys meet that goal, you get a
Oh, well,
sweater
we
in
should-
the
we
face
could win.
tomorrow that's representing your grade. So
Everybody bring
donation,
in,
guys.
I
Thank
don't
you
know,
so
20
much.
bucks. I don't know.
No way. Somebody, I mean, unless some kid brings in, if he's in a class of 15, you have to bring in a lot.
A lot. If we each brought in 15 to 20, we probably went pretty easy.
Yeah.
Anyway, minimize. Now that you can see the bottom, of it, you gotta understand that if you can't see it, it's because you haven't gone up high enough to see the bottom of something.
When you're trying to,
Yeah.
when you're trying to minimize.
So keep moving your Y's up until you can see something. That's what happened. We missed it with the 500. Okay, so when I minimize that, I get 5.419 and 553.58.
Yep.
What does that mean?
That means our radius is gonna need to be about 5.419.
The radius, centimeters.
In centimeters.
And that will produce a surface area of,
500.
that's what we've graphed, is surface area. So 553 is the best we can get away with for this thing. And just for the fun of it, what would the height be if I just want to look at these, I just want to look at a couple of these cans. If the radius is, as this thing prescribed, 5.42, almost 5.5. And the height would be what then? Remember your X is stored, so go back to your home screen and do 1,000. Divided by, and don't forget parentheses, pi x squared. Close the parentheses, and I get 10.84 for height. Do you get that? I plugged this in so I could get a height.
Yeah.
That's
Okay.
right.
All right. Do you notice something interesting here in the two things I just wrote?
They're double.
One is twice the other. This, if the radius is this, then the diameter is 10.84. Meaning your most efficient can will always be what I call square. Will always be far across.
Is that most efficient?
Because it will hold, and I realize we have 1,000, but any can that has a diameter, you will get more volume per surface area with a square can than any other kind. What I'm saying, square can meaning the same thing as across the very tall. That's what we just discovered.
So then why don't they do that? They're like, some cans are going to like,
Because it is not aesthetic. People don't want to drink a soda out of a can that's filled with soda.
It's true.
You know, it has to do with what people will buy. And people these days are buying skinny cans like the Red Bull cans. They like that better. For some reason, it appeals to them. Makes them, people like skinny and tall. The reason why we've always had kind of fat and squat cans is because of our football. Our guys that we value, when they get their pads on and their helmets on, are wide and squatty.
We got that.
People in Europe value their football players, who tend to be very lean and tall.
God,
Isn't that weird?
that's so.
Yeah, it's weird how our minds choose things that they find aesthetically pleasing based on other things. It's all mixed together. Anyway, that's the reason why I don't do it.
God.
Nobody likes to look at it.
So they try and get the best surface area that they can.
Yeah, they try to do that, but
With-
they also do it based on a whole bunch of statistical studies on what people will buy.
Yeah.
What they
So they
can
try
And
and
it's
find
worth
the
it to
mix
pay a little more for, if somebody will buy it, as opposed to rejecting yours for someone else's.
Gotcha.
All right. All right, see ya. Done with this one. We'll do some more tomorrow.